Hello, in this video, we are going to take a look at how we can use integrals to find the work done to pull an object up vertically. So we want to find the work that is needed to lift an object when the motion is vertical. So far, we've been working with a horizontal distance. Now, with a vertical distance, we're going to have a force that's due to gravity pulling down. So we're going to use force equals mass times gravity, where gravity is 9.8. Many times we might just leave g in the integral to just simplify things, or we can use 9.8. Suppose, to figure this out, we have a chain of length L hanging from a high platform. So here is our platform, and there's a chain hanging down. Very realistic looking chain there. And it has length L. To help us out, putting a scaling on this is helpful. So we're going to call the bottom of the chain 0 and the top of the chain L. We want to find the work done to pull the chain up. So we're finding work equals force times distance. And force is mass times gravity now. So work equals mass times gravity times some distance. Well, going all the way back, we have a mass of this chain where mass, going all the way back to the beginning, is density times volume. So needing to know some things about this density, this mass, in particular, we have a constant density rho being multiplied by some length of chain. So work is also equal to rho times L times gravity times distance. Rho is constant. Gravity is 9.8. It is constant. What we need to do to find work is find some way to express this length of chain and some other way to express this distance traveled. So we're going to break up our chain. And look at some tiny little piece of chain from xi minus 1 to xi. This has a vertical length of delta y. And what we're looking at is how much work does it take to pull this bit of chain from xi minus 1 to xi up to the top. Or actually, these should be yi, since we're talking vertically. So we're in vertical world, we use y's. So figuring out this work done for this little bit of chain, rho, our constant density and gravity, stay constant. And then the distance that bit of rope is being pulled, this distance piece, it is being pulled whatever this distance here is. But we know we're looking at the segment that's at yi, and we're trying to pull it up to be at a height of L. Well, basic subtraction says this distance here is going to be that length of the chain minus where we're looking on the chain, the yi part. So that piece there, L minus yi, is the distance. So D equals L minus yi is distance bit of chain or bit of rope is being pulled. So that goes in for our D, L minus yi. And then the length of rope, we're looking at a very small little piece of rope or a very small little piece of chain. So there are all our pieces defined. So if I want to find the work for all of this chain to be pulled up, it would be the work to pull up each small little segment of chain, the work to pull up this small segment and this small segment. So we add up all of our pieces of work of I equals 1 to n of each piece of work, bro G L minus yi delta y. And then we take the limit. We make those pieces as small as possible. And taking the limit will give us work. But this is also the integral from a to b of rho times g times L minus y dy. So that is our formula for finding the work done pulling chain up. Particular, this is for all of the chain being pulled up. We would say from 0 to L for all of the chain. From A to B gives us the chain in particular being pulled up, a small piece of chain. But there are other things we'll have to keep in mind that we're going to see in the next example. So looking at this example, suppose we have a heavy rope that is 24 meters long, and it hangs over the edge of a building 40 meters high. And it has a linear density of 3 kilograms per meter. So our picture, we have this 40-meter tall building. We have the chain hanging down. Well, we don't actually care how tall the building is. We just care how long the chain is, or the rope. It is 24 meters long. Bottom of the rope, 0. Top of the rope, 24. The work is going to be the integral from A to B of linear density times gravity times L minus y dy. This is just filling in the pieces. We're pulling up the whole rope, which is 24 meters long. So we're going from the bottom of the rope to the top of the rope. Rho is 3. G, we're going to leave as G. We could put 9.8 there. Does not matter. But leaving G for now. And then L is 24, the length of the rope, minus y dy. We are integrating with respect to y. G is just a number. So this becomes 3g 24y minus 1/2 y squared from 0 to 24. And when we plug in 24, which I will not show here, and when we plug in 0, plug in the upper and the lower bound, this integral ends up working out to be 864 G. So it takes 864 G joules of work to pull the whole chain up. Part B is, what if we're only doing 10 meters of the rope up to the top of the building? Well, work equals the integral from A to B, rho G L minus Y dy of this rope from 0 to 24. And we're only pulling up 10 meters. So we have the integral from (14) to 24 of 3G 24 minus Y dy. However, when we pull these 10 meters up, there's still 14 meters of dangling chain that also moves up, but doesn't go to the top of the building. So plus some amount of work for the bottom portion of our hanging chain. That also is going to move 10 meters, meaning there is some work to be done. The work for this amount of chain, though, we know here that there is again 14 meters of rope that's moving. We know it's moving 10 meters, and we know that for each meter of rope, it has a 3 kilogram linear density. So work for that bottom half of chain, since work is when the force is constant, force times distance, we have a constant force being done. So work equals force times distance. The force for the vertical distance is mass times gravity. And the mass is volume times density. Now the volume is our length of rope. That is just moving. Times density, times gravity, times the distance being pulled. For bottom half of rope, or bottom portion of rope, that volume of rope is, well, there's 14 meters not being pulled to the top. The linear density, or sorry, the constant density is 3. Gravity, 9.8, or just G. And the distance it moves is that 10 meters. So the additional work needed to move that bottom portion of rope is going to be 14 times 3 times G times 10. This will calculate out to give us the work that is done to pull only 10 meters of the rope to the top. Now, part C says a 20 kilogram load is now attached to the bottom of the rope. We still have that 24-meter long rope. But now there's this giant 20-kilogram load. The work done for just the rope, we've already calculated. The work for just the rope is the integral from 0 to 24 of 3 times g times 24 minus y dy. However, we also have this load, and it takes work to move the load. So plus some amount of work to move the load. Some scratch work on the side. Remember, work is force times distance. And force is mass times gravity. So work is mass times gravity times distance. We are told the load is 20 kilograms. G is 9.8, or we'll leave it as G. And the distance the load has to travel is the length of the rope. It has to travel 24 meters with that whole chain. So the load is going to be 20 times G times 24. And this expression will find the work done to pull that 20-kilogram load up to the top. We have work to do the rope and work to move the load. So a lot of the task with these work problems is thinking through the integral for the bit of rope that moves, but then is there additional piece that continues to need work done to move it? That's what B and C did. In the next video, we'll look at work done pumping liquids out of tanks, and it is a very similar integral for the lifting. But we will take a look at that in the next video.